we should have Julia Christina Costacurta. So she's a PhD candidate with Stanford University, and we have her workshop with the title Exploring Hidden Markov Models.
As Livia mentioned, my name is Julia. I'm a PhD candidate here at Stanford, and I'm going to be presenting today on exploring hidden Markov models. And this is my email down here. If you want to contact me, I'll drop it in the chat after the presentation. So to begin, I'm going to motivate kind of why we look at hidden Markov models with an example. This is the example. I'm going to call it Alice and Beth. It's very similar to like the classic Alice and Bob example, but I thought since we're at the Women in Data Science workshops here today, might mix it up a little bit. So suppose that we have Alice here, and Alice lives in a town where there's only two possible weather situations. So the weather can either be sunny or it can be rainy. So you know, like just for the sake of this experiment or this kind of setup, there's two weather conditions here. And now suppose that for some reason, Alice can't see what's going on with the weather. What Alice can do is she can reach out to a friend who's called Beth and say, hey, Beth, like what's going on with you today? And then for the sake of example, let's say that Beth can only be doing one of three things. So Beth is either coding, she is rock climbing, or she is reading a book. And if there's any other Bay Area grad students out there, you might notice I've based this on personal experience, but so say like Alice can't see the weather, but she can message Beth and see what Beth is up to. And now suppose that Alice does this for a week and has this series of observations about what Beth was up to on each of these days. And so Alice can kind of think about things and say, okay, suppose I want to know what the weather is. I can't directly observe it, but I do have this series of observations of what Beth was doing. And maybe I can say, okay, like, can I use the information I got from Beth to predict the weather? Because if Beth was rock climbing on Friday, it probably wasn't raining because that's dangerous and you shouldn't do that. And so, okay, like, does that mean that it was sunny? And so this is kind of where like the inspiration or like one way that we can use hidden Markov models, it's to predict things that we don't know about, given some sort of observations that we're able to make. So going into the hidden Markov model, here is our graphical model. I'll walk through just in case you haven't seen something like this before. On the top row, we have variables which are hidden, which means that we usually can't directly observe them. And these are in the tradition of graphical models. If they're white, that means you can't like directly observe. And we have a chain of hidden variables from Z1 all the way up to big ZT or Z big T. And then we also have observed variables that are grayed out, and that means that we do have direct access to them. And those are also of length big T. And kind of the really important thing about this graphical model is it shows us what dependencies there are between variables. So if we look at this kind of vertical connection here, this arrow, what this is telling us is that at each time step, the observed variable X is only dependent on the hidden variable Z. And this is a really important assumption behind hidden Markov models. And so what that kind of means in math is that if we want to compute the probability of an observed variable, and we are conditioning on a hidden variable, we don't have to condition on anything else. We can kind of cancel out anything else in that expression. And that is something that we're going to take advantage of when we go into more derivation types work. The other dependencies that exist in the hidden Markov model are between hidden variables. So you can see we have this horizontal arrow, and that is telling us that the hidden variables only depend on like the previous hidden variable. And if you were at the Markov chains workshop with Mackenzie, last month, you'll notice that this top, like the name hidden Markov model comes from the fact that this top row here is a Markov chain and it's hidden. So we can go into what we know and what we're assuming here, which we should do in every model that we work with. So what we do know, what we're going to say that we know is the probability of an observation given the hidden variable. So the probability of XT given ZT, which corresponds with this arrow here. We're saying that we know the probability of a hidden variable given the previous hidden variable, which corresponds with this horizontal arrow between our Z's. And just because we kind of have this special case in the top left corner where Z1 doesn't have any like dependence, we're going to just say that we know the initial distribution of that variable. If we're working with a really long time series, this ends up not being super crucial for calculations, but We're also assuming that the observed variables xt only depend on the current hidden variable, and that the hidden variables only depend on the previous hidden variable, like I mentioned earlier. And so going back to our example, what this would mean is that our activities, Beth's activities, are what we observe. So those are going in the grayed out bubbles. And the weather is what we're not totally sure about. And so what we know is that we know the probability that Beth is doing something given the weather. We know the probability of weather on one day given the weather on the previous day. And we also know the probability of weather on the first day. And what we're assuming is that Alice's activity only depends on whatever the weather is that day, and that weather on a given day only depends on weather from the previous day. And so with any model, you know, we have this trade-off. Is this a realistic assumption to make that the only thing that Alice's activity, or sorry, this should say Beth, but the only thing that Beth's activity depends on is the weather for that day. But, you know, like it's kind of this trade-off between, okay, we can have a simpler model that's easier to interpret, easier to work with, but we are going to have these assumptions that we're going to have to reckon with. But I think as long as we're aware of these assumptions, that's the most important thing here. And so kind of getting into how we can represent hidden Markov models, suppose for the sake of illustration that I have this chain of weather events as well. And so in the categorical case, which is what we're working with, where our observations take on discrete values. So remember, we said that Beth can only do like 3 things. We can represent our transition and observation probabilities that we assume we know using matrices. And so if we assume that the weather being sunny corresponds with a value of 0, and that the weather being rainy corresponds with a value of 1, we can write a transition probability matrix like this. And I'm going to quickly just run through like how I'm going to index this matrix just for, I'm going to do it in a way that makes it easier to code up later. But what I'm going to say is that this 0.8 value in the top left is the probability that it's sunny today, given that it's sunny yesterday. And this top right value is the probability that it's rainy today, given that it's sunny yesterday. So the thing that we're conditioning on, so in this case, that it was sunny, tells us which row we're going to index in. And then the thing that we're taking the probability of tells us which column to go into. And this is, again, just for like, you could also use like the transpose of this matrix and just index things differently. This is for the ease of coding later. And then similarly, if we assume that the activities that Beth is up to take on values 0, 1, and 2, we can write an observation probability matrix. And this one is going to be rectangular. This one can be rectangular if the number of observations, possible observations, and the number of possible hidden variables are different. So similarly, the thing that we're conditioning on is going to tell us the row, and the thing that we're taking the probability of is going to tell us the column. So if it's sunny today, I'm going to look in the first row. And if I wanted to find the probability that Beth is coding, I'm going to look in the first column. And then likewise, 0.2 here is going to be the probability that Beth is climbing today, given that it's sunny. Are there any questions about this setup before we get more into things?
I'm seeing nothing in the chat.
Cool.
Just yet.
Thank you.
Renee,
All right. Thank you, Manuel. Okay, cool. So the assumptions that we're working with, again, are pretty strong assumptions, but ones that are going to be very helpful. So we can say that the probability of observing like a chain of observed variables and hidden variables, we can split this kind of by using the multiplication rule for probability into the probability that of X conditioned on Z times the probability of Z. And then we can use our assumptions here to split these into a bunch of individual probabilities at each time point. So this is one kind of nice thing that we can do because of the assumptions that we've made. And then what that means is for sampling, since we know the probability of Z1 and the probability of ZT given ZT minus 1, we can just sample a sequence of hidden variables. And then we can use the sequence to sample our observed variables using our known probability distribution. And so that's what we're going to do now. So I'm going to quickly swap into Collab. And I think the link to this, you don't have to like code along if you don't want to, but the link will be posted in the chat for y'all if you want to follow along. And let me just quick pull up. I have a little cheat sheet for All right, cool. I'm just gonna wait for the link to show up before we keep going. I can also share it. So yeah, if you need that link, it's in the chat now. I know that one of the prior workshops used Collab, but just in case you haven't seen it before, one nice thing that you can do is you can go up into File and just make a copy in Drive, and that'll save a copy with your own changes. If you try to make changes kind of in my copy, it will not save them. So just to be aware of that. Are folks getting to the Collab link okay if you'd like to follow along with code? Awesome, thank you. Okay, so cool. So I'm just gonna go through. So like, first, if you would like to follow along, make a copy and Drive right here. And then I'm just gonna load up some packages. This stuff down here. So we're going to use the categorical distribution from Torch. And it is really nice, except for one thing, which is that it will only take in tensors as the input. So this is what is down here. This is just a quick set of helper functions to convert to and from tensors between NumPy arrays and tensors. So I'm just gonna play this. All right, cool. So we're gonna code first the sampling function for our hidden Markov model. So what we're going to do is we are going to come down here and recall, so this is our graphical model we're working with. And for our categorical hidden Markov model, I'm going to say that we need the number of states, the number of observations. So that's the number of possible values each of these things can take on. We have a probability matrix associated with transitions between our discrete states, a probability matrix associated with our observations, and then the distribution of that initial state. And I'm just gonna, for the sake of not being too confusing, just get rid of that. Okay, so then we're just gonna throw all of these variables into our class. And for our sampling function, the first thing that we're going to do is sample the hidden state and observation at time 0. So we need to start from somewhere. So what I'm going to do is, first I'm going to say, okay, my initial state is going to be a categorical. I'm going to sample from a categorical variable, and the probabilities that I want to put in there for my first state are going to be the initial distribution. So I'm going to first convert it to a tensor, and then I'm just going to throw my initial distribution in there and then sample it. So that's sampling from kind of a tensor distribution, which is, or sorry, from a torch distribution. And then for the initial observation, it's basically the same, but a little different. So now what I'm going to do is, and I'm missing a T. I'm going to go into my observation matrix and note that the row that we're going to index into corresponds with what we're conditioning on. So that's why I kind of set things up the way I did earlier. All we have to do is index corresponding with the initial state, which is what we're conditioning on. And I'm going to just turn that into an integer so I can index with it. Cool. So this should be sampling, and now it is sampling our initial state and our initial observation. So then what we can do is we can just store what we have. And then we are good for our first step. Luckily, we can loop over everything else. So then what we can do is for the rest of the time steps, I can say that my current state is equal to my, again, my current state. So I'm going to go into sample states and just grab the current one. And then for sampling my new hidden state and observation, I do something very similar to, as you might imagine, to the steps above. So we're going to do a new state. And again, we're going to index into the transition matrix with our current state. And then we are going to create a new observation, which is the same as up here, except we're now going to index with our new state. And so if we just store that stuff, sorry, live checking is hard. If we just store that stuff, we have created a sampling function. I noticed there's a question in the chat. What does categorical do? That's a great question. So, okay, I hope I addressed that that thing in the Q&A interface correctly. But the categorical thing is, so we imported up here. It's from torch distributions, and what it does is it basically creates like an object that is like the categorical distribution associated with like a vector of probabilities. So what's happening down here is we're saying we're going to create a categorical distribution, and it's going to like the vector probabilities is going to be our initial distribution. So our initial distribution here is just going to be a vector that is like going to have values, say if it has values like 0.1, 0.9, that means that it has 0.1 probability to take value 0 and 0.9 probability to take value 1. So that's what we're putting into our categorical object. And then when this sampling function just produces a single sample from that categorical variable. All right, does that answer your question? Do you mind maximizing the video? I don't know what that one means. Sorry. Oh, zooming in. Sure. I'm gonna. Okay. Is that? Oh, I see what you're saying. Yeah. Thank you. Okay. Cool. So this is our sampling function. So I can hit play on that. And then if you come back to this later, I do have a working solution that I confirmed works, and also just an emergency case in case I can't live code today. But this is our working solution. And then we can define an HMM and test our sampling function. So if we say that we have two like hidden states, so I'm gonna kind of refer to stuff interchangeably with like hidden states and like visible states, and then also like states and observations. So when I just say states, assume I mean hidden states, but if it's unclear, please ask. So assume we have two states and 3 observations, like in our example before, and we have a transition probability matrix and an observation probability matrix and our initial distribution. Then we can just throw all of those things into our categorical HMM object, and that will like initialize what we're trying to do. And then we can sample for 10 steps, and it worked. And then we can plot our sampled hidden states and observations. Cool. So just seeing if these kind of match our intuition for what we would observe. From our initial distribution, it's very likely that we are going to start in the zeros, like kind of 0 value state. Pretty unlikely we're going to start in the 1 value state. And we do see that, so we start at 0 here. And then once we are in that 0 state, we can look at the transition probabilities. It's pretty likely we're going to stay in that state. And so that kind of produces these wider blocks that are this purple navy color. And then for our observations, if we are in, so our top row here tells us that if we are in kind of the 0 state, it's very likely that we're going to have an observation of 2. And if we are in the kind of like one state, it's very likely that we're going to observe 0 or 1. And so we can kind of see that here. If we're in the 0 state, we see a lot of yellow, which is 2. And then if we're in the other state, we see 0. So, and then there's another question about real life applications. That is also a really great question. I'm going to answer that like towards the end, if that's okay. But if there's like a time constraint, just let me know. Cool. Okay. So now let's go back to our slides. If there are no questions about the code. Could I explain the bar charts? Yeah, for sure. So what this is doing, this is kind of just like a way to hack like the imshow function so that it shows you like basically time series data that takes on like discrete values. So this is like what I can also do is like if I do, and I realize this is, I don't really need to be doing this. This can just be like this, but okay. So what's happening here is like, this is like kind of the plot that we would see if we just threw this information into like the plot like function. It's basically jumping between 0 and 1. And another way to view that data is we can look at it with like this color, this like kind of color coding. So we can say, okay, purple is 0 and green is 1. And this is just another way to view this kind of like time series data that takes on only a few values, because this can be a little hard to like parse sometimes. But the way you view this data is really up to your preference. Let me know if that answers your question. Don't really understand how to interpret the plots. Yeah, so there's not really that much interpretation to do right now. But what I was trying to get at was that so this is, I should have gone through the colors and stuff first. So let me quickly do that. So the blue here, this top, that's my bad. This top plot here is like the hidden variables, and the bottom plot here is the observations that we just sampled. So the blue color is the value 0 if we like have the hidden variable be 0, and then the green color is if we have the hidden variable of 1, and then down here it's similar, but it takes on 0, 1, and 2. And so what I meant by kind of like, I just wanted to look at these plots and see if like what we're seeing here kind of makes sense given like what the probabilities were that we started out with. So we started out with the probability that like it's very likely we're going to start in state 0, and we do see that. So like this is our time axis down here. We start in state 0, we stay in state 0 for a while, swap to state 1 for a little bit, then go back to state 0, state 1, and then state 0. Which kind of matches with this idea that like we're very likely to start in state 1 from this 0.9 up here. We're very likely to start in state 0. My indexing is a little iffy, but we're very likely to stay in that state if we start in it. And then it's more likely we're not going to stay in the like 1 state for very long. Yeah, exactly. Yeah, good. So Claudia mentioned that with our example, the top would show the weather. So say like blue is like sunny and green is cloudy. And then the bottom would show what were our observations or what was like Beth was up to. So that's a good, good like interpretation. Thank you. Cool. Are there any other questions about the code? Or if there's a need for more explanation, please let me know, because I want to make sure this is clear before we move on. Why can values be 2 while probabilities are between 0 and 1 on the observation plot? Yeah, okay, cool. So the probabilities, so for observations, oh cool, thanks Valerie. Okay, So our probabilities can take on, so remember we say that we can take on 3 possible values with our observations, and 2 possible values with our states. So that kind of tells us that like with kind of the way that sampling occurs, we're going to sample values for our observations from 0, 1, and 2. And we're going to sample values for our discrete states from 0 and 1. And then the probabilities are just like the probabilities that we observe each of those values. So for instance, like this row here says that, okay, so remember the row corresponds with what we're conditioning on. So if our hidden state is 0, then the probability that we observe 0 is going to be 0.1. The probability that we observe 1 is going to be 0.1. And the probability that we observe a value of 2 is going to be 0.8. So the value is like the value of what we are observing, where like the probabilities kind of tell us the probability of observing a value, and the value can be like anything. Here we're saying like, okay, we're like saying that the values correspond with just like 0, 1, and 2. But cool, thanks. All right. Cool, so I'm going to move on. Okay, so I'm going to then go through, now that we have kind of our HMM set up and we're sampling from it, we can go, like there's this tutorial that has these 3 classic problems that we can address using HMMs. So the first problem has to do with likelihood. So given an observation sequence and a model, how do we efficiently compute the probability of observing the sequence given the model? It has to do with, the second question is decoding. So given an observation sequence and a model, how do we choose a hidden state sequence which is optimal in some way? And number 2 here is kind of the question that we were looking at when we were motivating, which is, okay, like, can I tell what the weather is if I only have what Beth is doing? And then we can also learn an HMM. So how do we just adjust the model parameters to maximize the probability of observing data given a model? So I will get kind of, so these are all from this very classic tutorial from the 80s when by Lawrence Ravener about hidden Markov models and applications in speech recognition. So Natalie, that is one application that hidden Markov models have been used for quite a bit. And the first one and kind of part of 2 are solvable using the forward algorithm. So that's what I'm going to go into next. So the forward algorithm has to do mostly with likelihood computation. And suppose that we're trying to compute this probability on the left right here. So the probability of a sequence of t observed variables and like the most recent hidden variable. And you can imagine that like if I just sum over all of the possible hidden variables, it'll spit out the probability of x1 to t. So that's kind of why we're looking at this particular expression. So what we can do is we can throw a zt minus 1 into our expression, sum over it, and then separate out xt and like the rest of our x, like our series of observations. So these 2, we have not used anything about hidden Markov models yet. These 2 sides of the equal sign are totally just the same. And then by the multiplication rule, we can kind of telescope out this expression. And again, this is not using any assumptions yet. So we can start by first taking the probability of xt, conditioning on everything else, taking the probability of zt, conditioning on the remaining stuff, and then taking the probability of whatever is left. So these 2 lines should be exactly the same, assuming I typed everything correctly. But then we can use our assumptions. So remember that our first assumption that was that xt only depends on zt, and zt only depends on zt minus 1. And so this is where we can take advantage of those assumptions. So what's coming up here is we're saying, okay, if we have xt and zt shows up in the conditioning, then we can get rid of everything else. We don't like care about anything else. All we care about is zt. And the same thing with zt and zt minus 1. And so what that gives us is the sum over zt minus 1 of this probability of xt given zt, which we know, the probability of zt given zt minus 1, we also know this, and then the probability of x1 to t minus 1 and zt minus 1. And if you have an eye for recursions, you'll notice that this is 1. So this is, sorry. So this defines a recursive relationship by which we can find these values for successive values of little t. And this is called their forward algorithm. So if we let alpha of zt equal this value on the left-hand side here, this gives us our alpha of zt equals the probability of xt given zt times the sum over zt minus 1 of the probability of zt given zt minus 1 of alpha of zt minus 1. So we know the stuff that is not highlighted, and the stuff that is highlighted we can calculate recursively. And one way to think about this is that this summation is propagating our distribution forward. So it's kind of taking advantage of the fact that we know how things are like distributed in this like Markov chain. And then our piece here is the corrector, which accounts for the evidence xt. So note that over here, we're not worried about our observations at all, but we do have observations and we should use them at some point. So then we use them over here. And you'll note that we do need a base case. So the base case alpha of z1 is going to be the probability of x1 given z1 times the initial distribution that we assume that we know. Cool. So now what? So now we have alpha of zt, which is equal to zt, the probability of zt in x1 to t, and we have that defined via a recursive relationship. So once I can calculate alpha of zt, oh, sorry. First, I just wanted to get into like notationally, like this has a lot of different names. We can call these things the forward messages or the alphas. And then the calculation of those values is called the forward pass or alpha recursion. Different books say different things. And so we can normalize, which gives the filtered posterior. So if we're curious about the probability of a certain state, of like hidden state given observations, and recall, like, just take note of the indices here. This is little t. We're gonna take the, like by Bayes' rule, we can say that's the probability of both things divided by the probability of x1 to t. And note that x1 to t, like this probability is going to be the same for all of our zt's. So we can just, that's the same thing as just normalizing alpha of zt. The other thing we can do, which is really what we were setting out to do, is some sum over zt's to give the likelihood. So if we want the probability of a series of observations, x1 to t, we just run the forward algorithm. Then at the end, sum over all of the possible z big T values, which is the same thing as summing over the possible alpha values at time big T. And that'll give us the probability of data given a model. Are there any questions about this before we're going to go into Collab and code this up? So we'll pause for questions. And the questions have been great so far. Thank you. Nope. Okay. Thanks, Manuela. Okay. Oh, cool. Could I explain the filtered posterior again? Yeah, for sure. So the filtered posterior, this is just like we're trying to find, you know, if for whatever reason you want to know the probability of a hidden state given just like the previous observations and like current observation, by Bayes' rule, we know that like if we have a conditional probability, that's the same as the probability of both things divided by the probability of the thing we're conditioning on. And well, we can notice that the top here is the same as like our alphas. So we can kind of put alpha up here. And then this bottom thing, the probability of x1 to t, that does not like, that's going to be the same for all values of zt. Because there's like no z in this expression, right? So this is going to just basically be a constant. And so what we can do is say that like if we just normalize alpha of zt over the possible values of zt, that'll just give us this probability here. Hopefully that helps. Cool. I'm going to go into Collab again. Let me just get set up with my cheat sheet again. All right, cool. So we can code now the forward pass. So I've copied it over here, just in case anything, like we want to remember what we're dealing with here. So the first thing that we can do is, again, since this is a recursive relationship, we can calculate alpha of Z1 first. I'm going to do this with like some loops. If there are definitely cleverer ways to do this, but just for like code readability and for me live coding right now, I'm going to do it in like maybe a little bit of a simpler way. So for our first time step and for each of our alpha values, first thing to note is that our alphas here, they're going to be rectangular, like this is going to be a rectangular array. And the shape that I'm giving it is the number of states. So in our case, 2, okay, sorry, sanity check, 2 by the length of our observations, which is big T. So at each time step, which is big T, of length big T, at each time step, there's 2 possible values of alpha depending on which state we're curious about. So what I can do here is say that our alphas at time 0, so our first time step, and for each state are going to be equal to, and we have this equation here. So we have the probability of x1 given z1. So we're going to go into our observation matrix and we're going to index. So the thing that we're conditioning on comes first. So that's S, that tells us the row. And the thing that we're taking the probability of is our observation. And we have observations when we're going into the forward pass. So I'm going to take the first observation and put that in the second spot. And then we can multiply this by the probability of observing the first state. So that is going to be so that is just indexing to our initial distribution to position S corresponding with the state that we're currently dealing with. And I have the colon here just because earlier the categorical like torch object likes to take like a 2D thing. So this is really just like a 1 by number of states matrix. Okay, so this is our first set of alphas. And let me know if there are any questions about that. But I'm going to go into the next set of alphas. So now we're going to compute the alphas for a given state and time point. So we're going to first take our kind of probability sitting out front here. So this is so this is the current state that we're in, S, which we're conditioning on, and then the observation at time t, or xt here. And then what we're going to do is multiply that by the sum. And this is just like, this is maybe a slightly like way without going into another for loop of computing the sum. Note that we're summing over the values possible values of zt minus 1. So if we just don't really index into those like specific, like if we don't index into specific values there, we can kind of just sum over everything. And maybe if I type it out and then explain it, it'll make more sense. But what this is we're going to take the probability of observing zt given zt minus 1. So that's this. So here we're saying that we're conditioning on any zt minus 1 value. And the next z value is going to be zt, which is our state from up here. And then we're going to multiply that by the alphas of zt minus 1. So our alphas, the first index corresponds with the numbers with possible states. The second index corresponds with time. So I'm using the time index. I'm not going to use the possible like z value index, because then this is basically taking care of this summation up here. And if you need clarification there, just let me know. Okay, cool. So I'm gonna just run this, and then we can put it as a function of our HMM categorical object, and then we can test our forward pass. So I'm just gonna throw like a sequence of things that I'm going to say we observed, like fake observations, into our forward pass, and we can see if stuff makes sense. So these, just for clarity, these are the transition matrix and the observation matrix that I defined earlier, just typed out. And so the first thing that we observe is a 2. And so remember that we made it very likely that we would start in the 0 state. And once we are in the 0 state, it is very likely that we observe a value of 2, right, from this value here. And so the model, so like the forward pass tells us, okay, it's like super likely that we are in the 0 state at time 0. And then at the next time point, we observe a 1. And so there's 2 cases that could lead to this value of 1. Either we go from, like, assuming we're starting in the 0 state, I guess, but like we can stay in the 0 state and observe a 1, which we will do with probability. Like, it's pretty likely we're staying in the 0 state. But if we're in the 0 state, it's relatively, it's relatively unlikely that we're going to observe a value of 1. Or we can transition to the 1 state and observe 1. So transitioning to the 1 state is relatively unlikely. But if we are in the 1 state, it is more likely that we observe a value of 1. And so that's kind of why I think, like, with this forward pass, these values are pretty similar, just because it's not totally clear, like, which state we're currently in. And we can kind of, I'm not going to work through the rest of these, but if you would like to, they're here. And one thing to point out here is that these values are getting pretty small. As you might notice, there's only 5 time steps here, and already the values are getting quite small. And this is a known problem with doing the forward pass. And so what people often will do is they'll work in log space, because in log space, multiplication turns to summation. So I'm not going to go over that today, but if you would like to look it up, often people work with like log space numbers, just so these calculations don't deal with underflow when these values get super small. And there's a question. Is it possible to explain again how to find alpha? Sure. So so this is like the kind of recursive relationship we have to find alpha. If we have time at the end, I can go through how to find this recursion again. I'm not sure if that is what you were wondering, but yeah, just for the sake of time, I'm not going to go over the recursion again because the slides will be available after today. But if there's time at the end, I can. So I'll leave that up for now. Cool. Could you please explain again how to interpret the forward pass output array? Yeah, for sure. So what's going on here is this thing here is our unnormalized probability that we are in state 1. So, okay, let's go back here. So remember that, like, this probability of zt given x1 to t is kind of proportional to alpha of zt. So what that means is that, like, this value here, this is kind of, these two are alpha of, like, at time 0. And this is like, so this value is the probability that we observe, like, the 0 state and our time series that we put in, x1 to t. And then this value is the probability that we observe the 1 state and our observations. I guess I'm using observe a little liberally here, but so this is the probability that we are kind of in state 0 and observe, like, x0. This is the probability that we are in state 1 and observe x0. And so what this is telling us is that it's really likely that we are in state 0 at time 1, given, like, the observations we have up until that time point. So, like, that's kind of, if we go back here, that's like, if we condition on the observations up until that time point, the alphas tell us how likely it is that we're seeing, like, a particular, or that we're in, like, a particular hidden state. Okay, I'm gonna jump back in just for the sake of time. But please let me know if that wasn't clear and we can talk more about it. All right, cool. And I'm going to go through this a little quick just because, like, trying to leave a little time for questions at the end. But you might imagine that if there's something named the forward algorithm, that leads to the assumption that there would be something called the backward algorithm as well. Now, suppose that we're dealing with a different problem here. So this, instead of finding the value of probability of ZT given x1 to t, we want to know the probability of ZT given all of our observations. So that would be smoothing. And so it's kind of called smoothing because instead of only looking at like a limited number of our observations, we're looking at all of our observations and we're trying to find the most likely state, like hidden state at a particular time step, given all of those probabilities, or sorry, all of those observations. So what we can do is again, kind of break things up like we did before. And we can again use use our multiplication rule to split something into, to split this into the probability of ZT and x1 to t, and then the probability of the other stuff conditioned on ZT and x1 to t. And we can actually get rid of like x1 to little t in this expression, in this like condition. This is a little less clear maybe than the other cancellations that we were doing. I'm going to kind of punt on this one and say that like, if you would like to look into this, you can look into like graph separation as to why we can say this, but just kind of take it as a given for now. And this is going to give us, so you might recognize this expression here is our familiar, our alphas, our forward messages. This thing here, we're going to say is beta, which is our backward messages. And so our forward messages contain our past and like current information, and our backward messages contain our future information kind of conditioned on our current information. And so if we want to get into the backward algorithm, so say I want to calculate this value, we can again kind of sum over all possible ZTs and just throw that into our expression. And then by the multiplication rule, we can expand stuff out. So we're going to condition on xt given everything over here. And then everything else is conditioned on ct minus 1. And then using our assumptions, this is like going back to the assumptions that like maybe are a little easier to deal with, but we know that there's ZT, we're conditioning on ZT, so we can throw out everything else in this expression. And then, okay, so from there, we can expand things out a little bit more. And we can get rid of this like conditional. So this is kind of the like reasoning that I was punting on a little bit. So just take my word for that one. And we come up with another recursive relationship for the backward pass. And I'm not going to code this one up, so don't worry, we'll still end on time. But I just wanted to show you kind of where there's a forward pass, there's a backward pass, and they can be used together to find some pretty useful information. So this is our beta recursion, our backward pass. So if we let beta equal this conditional probability here, we can kind of define our betas this way. And note that like we're kind of stepping backwards. So the beta on the right-hand side is like beta of ZT. The beta on the left-hand side, we're discovering beta of ZT minus 1. And so this is kind of like cool because the betas, they're a backward pass because you're kind of going backwards through our data. And the base case beta of Z big T is equal to 1. One way to think about why this is the case is if we plug big T, or if we plug T equals 1 into here, that kind of empties out our observations, and all we're left with is the probability of like nothing, like conditioned on ZT, which since we're conditioning on has to be true. So our base case is 1, and then we can work backwards. All right. Cool. So these are our backward messages, our betas, and calculating these is called the backward pass or the beta recursion. And I see that there's a question about the forward pass. I will get to that kind of like, well, we can go back to kind of the code part at the end. And then about like, unlike the alphas, our betas propagate backwards in time, like we pointed out, and they can be run in parallel with the forward pass, which is really nice because you can save a lot of time that way. So if we have our alpha and beta messages together, this constitutes the forward backward algorithm, and that helps us calculate the smooth posterior. So if we want to, I know this is a lot of math, but basically if we want to calculate what we were getting at earlier, which is the probability of a hidden state Z little t given all of our observations, we can kind of use a combination of Bayes' rule and throwing in Z little t down here. Or sorry, this is just Bayes' rule. So we can say that's the probability of everything occurring divided by the probability of just our x1 to big T occurring, which we can do by summing over z little t. And then we can split things up into pieces that correspond with our betas and our alpha values. So this expression on the right here is how we would calculate the probability of z little t given all of our observations. And you can think of like how this might be more desirable than calculating the value of z, or the probability of z little t given only part of our observations, right? If we have access to all of the observations, might as well use them. And note briefly that this is not the same thing as computing the most likely sequence of hidden states, all of them together. This can compute kind of at each time point what is the most likely z little t, which is not the same as the most likely sequence. And that kind of brings me to the end of like my content, but so I'm going to go into like a little more, we can talk a little bit more about the code and the alpha values. But just like if you're curious about the kind of question that we just left off on, the most likely sequence of hidden states given the observations, you can look into the Viterbi algorithm. If you want to learn how to train hidden Markov model parameters, you can look into the expectation maximization algorithm that's also called EM. And then some book recommendations. These are kind of classic books with chapters on like hidden Markov models and EM. And then also there's a quick plug for Stanford teaches a probabilistic graphical models course here that has really nice course notes. And then Neuromatch Academy, which my advisor is affiliated with, also has a really nice notebook, like Jupyter notebook that you can work through that has examples for hidden Markov models. So that is the end of my prepared content. I will go back to alpha things just to kind of, so I think most of the questions are about interpreting the probability, like the alpha values. Yeah, okay, okay, let me go back to that. So anonymous attendee at 11:50, you have a very good question. Why don't the probabilities of state 0 and state 1 add to 1 in the forward pass result if there are only 2 states? That's a very good question. So what's going on here is recall that our alpha values are this probability here, this thing. So the way that I was interpreting them was through the filtered posterior, which these values should sum to 1. But basically what's going on is the alphas are not normalized yet. So like the alphas are basically like an unnormalized version of these values. And so the alphas will not sum to 1, but we can normalize them and then get these values, which would sum to 1. Hopefully that helps. And then someone asked, could you explain how to interpret the probabilities at time 2? Sure. So yeah, so the probabilities at time 2, I mean, so we observe the value of 2, and kind of the way I set up these probability matrices like this for a reason. And that is whenever we observe 2, it's like super likely that we're in state 0, right? So like from our transition probability matrix, we see that like if we're in, state 0, it's pretty likely we stay in state 0. If we're in state 1, it's not like totally as likely that we stay in state 1. And we also see from this top row up here that like, this top row up here, okay, it's not going to let me highlight just the top row, but it's super likely that like we observe state 2 given that we're in, or we observe 2 given that we're in state 0, right? So that's kind of like why it's more sure in this step that we're like at state 1, state 0. Let me know if I like flubbed any of the numbers there, but basically whenever we observe 2, because of like how our transition and observation matrices are set up, like the model is going to be pretty sure, like forward pass is going to be pretty sure that we're in state 0. And then for the attendee who was curious about how we find alpha, so the alphas come from, I'm not going to totally like step through this again, but the alphas come from the fact that like we're curious about the likelihood of our data. And so one way that we can approach this is if we find these values, we can just sum over all the possible values of z little t, and that will give us the probability of our data under our model. So we kind of go through this like derivation to find a recursive relationship. We find a recursive relationship, which is here. And then we let alpha be like basically alpha of ZT basically be the thing on the left. And this is kind of how we find the alphas in calculation wise. And then Natalie, I did not forget about your question. Some real life applications of hidden Markov models. So the tutorial by Lawrence Ravener talked about speech recognition. So that is kind of like, that's like one big area. Hidden Markov models. I mean, like, so I use a type of hidden Markov model in my own work that is an autoregressive hidden Markov model. And what that is basically like, it has arrows that indicate time dependence between the observations as well. So that is kind of like what an autoregressive hidden Markov model is. I use that for, we have a model that analyzes mouse posture, like posture data of mouse videos. So the hidden variable in that case is what is the mouse doing? And then the observed variable is like, what is the posture that the mouse is performing to do that action? So for example, if the hidden variable is that the mouse is like running or something like that, then the observations would be like the recording that we take, like the video data that we have, like where I guess like the mouse is running, but the observations are like the pixel values or in my case, like principal component values of the video. Yeah, there's a lot of different, I mean, like I think HMMs have been used in a lot of cases. I was like scrolling the Wikipedia page honestly yesterday, and there's also been used in like weather prediction. They've been used in like protein stuff. So just like a lot of different applications because they've been around for a while. So I think like a lot of fields have tried to use them. But I hope that answers your question. Thank you for being patient. And we are at 12. So if you have any more questions, please let me know. I'm going to stop sharing my screen. But yeah, thank you all so much for your attention. Oh, I'm still in Keynote. Okay. Thank you all for your attention. And yeah, let me know if there's any questions.
Thank you so much, Julia. And thank you for providing that insight related to hidden Markov models. I think it's an area where it's still kind of a mystery for some people. So I think you demystified a lot of content related to hidden Markov models. And you answered all of the questions. So there are no questions that I'm going to moderate, but if there's anything that comes up, we will definitely reach out to Julia offline. Thank you so much, Julia.